Hi, my name is Talha, and welcome to this demonstration of an RSA shared prime factor attack. In this project, I simulate a real-world RSA vulnerability where two RSA key pairs share a prime factor in their modulus. This breaks the mathematical foundation of RSA and allows attackers to recover private keys. The script is implemented in Python using PyCryptodome library. It is structured into modular functions to handle prime generation, RSA key construction, shared factor detection, and private key recovery. All the cryptographic logic I have cleanly separated to keep the code maintainable and logically organized. This design meets the functional requirements by generating multiple RSA key pairs with different key sizes. I've injected a share prime into the selected keys to simulate real vulnerability. I've used the GCD to detect the weak moduli. And I've also done a demonstration of recovering the private key and the decryption process. From a security standpoint, the code simulates a real exploit scenario and shows how an attacker can go from public moduli to decrypting messages if weak primes are used. Now, I just want to note that moving along from here, I'll be using the word prime because that's what I've designed it. But by that, I just mean a prime number. And here I begin by ensuring that the required library is available. The Cryptodome is crucial because it provides utilities for generating large prime numbers and computing modular inverses, both which I've used. So the installation here the installation line here is essential for replicating this project in any Python notebook. Next, I would say starting here, I import the libraries, the crypto.util. Imported numbers from here this is used to generate the prime generation, the prime numbers, and the modular arithmetics. And then the GCD from math library, this allowed me to test for common prime factors between the RSA moduli. And lastly, the default dictionary from collection. And this enabled me to group vulnerable keys cleanly based on shared primes. So this would automatically initializing a set when a new prime is encountered, right? Then I would go to this first function, and this is just a simple function that gets the prime number. I call it when with a specified bit size, and I receive the secure random prime number. So this will be used to generate both the secure and the intentionally vulnerable RSA key pairs. The reason I abstract prime generation to its own function is to create modularity and clarity. It allows me to reuse this logic wherever I need to generate a new prime without just duplicating the number. Now we have here, I have generated the RSA key. So it accepts an optional prime called shared prime. And this is to stimulate the key reuse across different key pairs. So first it selects P, either a provided shared P or it generates a new secure one. Then I have ensured that Q is different to the prime P when generating. Uh, Now this is crucial because the same prime twice will make the key insecure, right? And then I constructed the other components. Here, the public exponent E, and this must be co-prime to the Euler's totient. And for the RSA to work correctly, you're right. I begin with a very large number, and I think this is commonly used. And if it doesn't work, I increment it by two, and then I would just have in case there's no E found, then I raise an error here. And this process ensures that the generated key pair is valid and secure. Then I compute the D, the private exponent, using numbers.inverse. And this finds the modular inverse of E with respect to the Euler's point, allowing RSA description function to reverse the encryption later on. And then I return all the calculated stuff. Now, next I have the find shared factor. So this function is where I check every pair of RSA moduli to identify the shared prime factors. If if two keys share even a single prime, it creates a major vulnerability in RSA because the private key can then be reconstructed. So here what I do is I first define an empty dictionary called shared factor to store all the moduli that share a prime. I use two for loops to go through each unique pair of moduli. And I've done so where j is greater than I, so I can avoid the duplicate comparison. And then for each pair, I calculate the G, and and then what I do with it, I've made sure if G is greater than 1 and not equal to any of the modulus, then G is the shared prime factor. And then I store them in the library that I created, and the library is just returned. So this technique is computationally cheap and it's very effective. And it's also used in the real world to detect if there are accidental prime uses. All right, next is the recovering a private key. Here, after I've detected a shared prime, this function reconstructs the RSA private key. I divide the n by the known shared prime to get the q. Then I calculate the Euler's tOint, or totient, sorry. And finally, I compute the d, which is the private exponent. So that would enable the decryption process. And yeah, this function models a real-world cryptographic break. With just NE, the shared prime, I can fully recover the private key D. Then I have the actual demonstration, the full demonstration, right? In this function, I first create a shared prime number which basically simulates a known RSA vulnerability where multiple key pairs share one of their factors. I then generate four key pairs, two intentionally insecure ones, these two, and they even have the shared prime. And then I create two secure ones, and they're generated independently. And after the keys are created, I extract the modulus n from each key and store them in a list called moduli. I then pass the list to the find shared factors function, and it basically lists the GCD detection. That's what it does. And it finds or searches for the shared primes, right? And then stores it as shared. And if a shared function is, if a shared factor is found, then I create a dictionary called prime two keys, and where each shared prime is mapped to a set of key indices or the indices they use. And then I use the default dictionary set because it makes this grouping efficient by, automatically creating an empty set for each new shared prime that is encountered. And then I have this loop here, and this loop just adds both the key indices to the set associated with the shared prime. So it's grouping all the vulnerable keys for further processing, basically, right? Then for every shared prime found, I loop over the indices. I loop over every indices of the affected key pairs, right? I extract each of the RSA keys modulus, and then I recalculate the entire key pair. I rederive the Q, the Euler's totient, and I recover the private exponent D. Right? So now that I have D, so like at this point, I've rebuilt a valid RSA private key purely from the public parameters and one leaked prime. And this clearly shows how devastating a shared prime vulnerability can be. And to complete the demonstration, I print the reconstructed RSA parameters to validate the private key has been recovered successfully or accurately rather. And this includes the original primes, the modulus, the private and public exponents, and the reconstructed keys. I then prompt the user to input a message, and this is like simulating a real-world encryption, where encrypted message being intercepted and then decrypted by the attacker. So I take the user-supplied message, I encode it into bytes, and then I convert it into integers. I then encrypt it here using the modular exponentiation. Then I decrypt it using the private key here, the private key, and I finally what I do is I turn them I convert the results back into bytes first, then into string, and then I print out the decrypted message. Right? Now, if the decrypted message matches the original output, the original input, sorry, the one that the user inputs here, if that matches the output here of the decrypted message, then the attack has been successful, right? And before I actually run, I have to mention that my script includes some key safeguards, like the P not equal to Q in the key generation right here. So I ensure that Q does not equal to P, right? I've also made sure that for the Euler's totient, that the greatest common divisor between E and the Euler's totient is 1. And I've also handled the input. So if there is an error, I also have a fallback message, right? And what I would say is this RSA shared prime attack project it powerfully illustrates how fragile cryptographic systems can be when implemented or when implementation details are ignored. If prime numbers are reused even once, an attacker can extract the private keys and they can decrypt the communication. And this project hopefully provides not only a demonstration, but a strong educational tool for understanding real world crypto vulnerabilities. And I would say the main takeaway would be that always use strong, unique, and securely generated primes when working with RSA. So I'm just going to run this code now just to show. So it prints out the keys, so keys 0 and 1, so that would be the keys. Where have I created them? Yeah, here. So this one, key 0 and key 1, those are the ones that have, and this is the shared prime that they have. Also printed out the parameters. So if I were to input a message like how are you? Right. So how are you? The original message and the message as integer. This is the encrypted ciphertext. And then I have successfully decrypted the original message, right? Here, if I say I am well, okay. Yeah, here's the original message, the message in integers, and then encrypted, and then here it's back to decryption. And I've also printed the parameters for this key as well. So that was my entire demonstration, and I would like Thank you for watching.